So today we are going to discuss the different algorithm or architecture used in analog digital converter to convert analog signal into digital signal. The first one, which is quite popular, is called a successive approximation analog digital converter. As the name implies, the algorithm, the architecture of this ADC tries to approximate the analog signal closer and closer according to the bit. So it approaches from I think from the most significant most significant bit. Most significant bit is the leftmost bit. Yeah. Then approach towards the least significant bit and slowly approaching until as close as possible to the analog value. So how does it know whether it has the value, the digital value is close enough to the analog? Is by using this comparator. Okay? So here we see it has a comparator. So first, the analog input is being sampled and hold, yeah, with SHA here, sample and hold amplifier. Then it is being the successive approximation register here will input value, for example, first approximate with the most significant bit, and then it creates an analog value out of it, yeah, to convert that digital value to analog signal and then compare the value. So if, for example, it has the analog value is larger than the approximated analog value from the DAC here, then it should then it will know that it should add more value to the digital bit. Okay, then it goes like that, yeah, in a repetition until the value is close enough. Yeah, of course, then it will depend on the resolution of the ADC. So the more the bits you have, the closer it can get, so the higher the resolution of the conversion. So the final approximated digital bit will become the digital output going out here. Okay. So this is called, that's why it's called recursive one-bit subranging architecture. So for example, here we have an analog input at this level, yeah, between the negative full scale and positive full scale. This is, for example, an example for 4-bit successive approximation ADC. So it has only 4 digit. So the first one, the most significant bit will be put at 1, yeah, at 1. So then the most significant bit means that if it is 4 digit, then 1 0 0 0. Okay. So this we have 4 bit. So first is it approximated 100. Basically, if for 4 bits, then the maximum is 16, right? Or 15. Yeah. So if the most significant bit is switched on, or it has a 1 value, means that it has a value of 8, right? Or half of the most significant, half of the total value, half of the full scale. That's why here it is switched on and it has this value, at the half of the range between minus negative full scale and positive full scale. Then it compares, it goes to the comparator. So it knows that it is still less than the analog input. Then it tries to switch on the second bit. Yeah, so it tries the second bit here. So it becomes how many? 8 plus, this is 1 times to the power of 2, 4. This becomes 12, right? So then 12 is somewhere from 16, yeah, 12 out of 16. So because the total, if it is on all the bits, then the total value will be 15 or 16 range. So 12 is more or less here, 3/4 of the range from negative full scale until positive full scale. Yeah, so this is the second approximation. And now the value, the approximated analog value from 1100 is higher than the analog input. So that it knows then this is supposed to be switched off. The second most significant bit is supposed to be switched off. So in the third approximation, in the third period 3, so this one, the second bit is switched off, the first bit is switched on, yeah. Then it will test at the third bit. It will switch on the third bit, yeah, so it becomes 1 0 1 0. So this becomes 8 plus 2, right? 10 out of 16. So here we see that okay, it is still less than the analog input. So this is true then. So in the next period, the period 4, then bit 3 is switched on. So 1 0 1. Then it will switch on the last bit, yeah, of the digital value. So the least significant bit, the LSB, the bit 4. So it tries now to approximate it as 1 0 1 1 or 11 out of 16. So when it approximated it at S11, we see that then the value is high or more similar. Yeah. So this is become then the conversion value of that analog input. One, this is the conversion is considered complete. 1 0 1 1. Okay. So then it starts with new conversion for the next analog input. Yeah, starting at here. So this is how successive approximation work. So it approximate the analog input from the most significant bit. The most significant bit is being converted into the digital analog into analog signal here. You see here. Then compared with the analog input. If it is still less, then it will switch on the second bit. If the value is then higher, then it knows that that bit should be switch off. The second bit should be switched off. Then it turns on the third bit. So if it is large, if it is larger, if it is larger, yeah, sorry, the second bit, then should switch off the second bit. Then the third bit is turned on. If it is still less, then it will switch on the fourth bit, etc., etc. Yeah, depending on how many bits you have. If you have 8 bits of analog digital conversion, then your approximation will be closer to the analog input value compared to if you have less resolution. Okay. So the rising or falling edge of convert starts, pulse resets the logic. This is the conversion here. From here, start convert means when it is rising, it means then it knows that it has to start the conversion. Then falling or rising edge begins the conversion process. Bit comparison is made on each clock edge. As you can see here, on each of this clock edge, then conversion is made or approximation is made. Conversion time equals number of comparisons or resolutions times the clock period. So if you have 4 bit, yeah, then the conversion and then your clock is, let's say, for example, 1 megahertz. For example, yeah. 1 megahertz, it means one pulse is about 1 microsecond, right? One pulse is 1 microsecond. Here, the period of one pulse is 1 microsecond. It means that if you have 4 bits, then one single conversion will require 4 microseconds. So it means your sampling per second will be 1 million divided by 4, right? 1 million divided by 4, because your pulse is 1 megahertz, right? Is 250 kilohertz or 250 kilo sampling per second. Your conversion rate will be 250 kilo sampling per second. Yeah? So if you put higher resolution, 8 bits, let's say, then your clock is still 1 megahertz. It means then your one conversion will take 8, yeah, times 1 microsecond, so 8 microsecond. So your conversion rate or your of sampling of analog digital conversion will be 1 megahertz divided by 8, yeah, or how many? About 125 kilo sampling per second. So this is something which is trade-off. The higher usually, the higher resolution you want to have, from the current conversion, which will means that your conversion time will be longer. So it's not as fast as before. So if you want very fast, then usually then you will sacrifice the resolution. Okay, because the other, or if you don't want to lose time, if you want still to have similar sampling rate, similar conversion rate per second, what you can do is to with a higher resolution, what you can do is to increase the clock, to increase the clock of your digital circuit. The accuracy of conversion depends on the digital analog to conversion linearity and comparator noise, because here it depends so much on this DAC as well as the comparator. So if there's noise on this comparator of M circuit or the DAC, then accuracy will decrease. So this is an example, again, another example, but in previous slide, we see it from the clock perspective, from the timing perspective, now from the value perspective. So for example, we have 0 to 10 volt, full range, full scale range, and it is a 4-bit also resolution. The analog input is 6.428 volt. So first, the first bit, the most significant bit is turned on, 1, which will be equal to 5 volt from the full scale range. So is the input value larger than 5? Yes. So if it is larger, then you know that this has to be turned on. Yes. Okay, then you turn on the second bit. So second bit will be 1, how many? 8 plus 4, 12, right? 12 divided by 16 times 10, or 3 divided by 4, 7.5 volt. Is the voltage larger than 7.5 volt? Yeah, this one is larger? No. So you know then the second bit should be turned 0 or switch off. Then you turn on the third bit, the third significant bit. So the value is 1 is 2, right? 2 over 8 is 1/4. 1/4 of is 1.25, 1.25 volt plus 5 volt. Is the value is larger than 6.250? Yes. If it is yes, then you know that the third significant bit should be turned on. Then the least significant bit, or the fourth bit, will be turned on. The value is how many? 0.1 half of 1.250, so 0.675. Then is the value is larger than 6.875 here? No, it's not, so it's less. So you know that then the last bit, the fourth bit, should be switched off. Then the final approximation will be 1010. So if we convert this, let's see, let's calculate. Anyone can help me with calculator? So this will be 8, right? This is 2. So 8 plus 2 equals to 10. So 10 out of 16 times 10 volt, right? Or 5, 8. So this is 6.25 volt, approximating the 6.428 volt. So the accuracy, the error will be this minus this one. So about 0.2, 0.1 something, 0.1 something volt. Okay, so if you want to have less error, of course, what you can do is increase the resolution into 8-bit, for example, or 6-bit. But then you will need more time to convert. So this is how successive approximation works. The advantage of successive approximation is it is low power. So for 12-bit with 1.5 megasampling per second ADC, it requires only 1.7 milliwatt. And it has higher resolution. For it can reach up to 16-bit for 1 megasampling per second. And in terms of fabrication, because you only require register, you only require here DAC, sampling and hold, and then comparator. So quite few subsystems. Then you do not require large die in terms of chip. Yeah, so you know that in microelectronic fabrication you have a wafer area. Maybe sometimes I don't know if I have discussed about this in sensor class. Yeah. This is usually in microelectronics IC fabrication. This is the diameter is either 4 inch, yeah, or 10 centimeter. Usually this is used in research, but in industry usually they use larger, up to 8 inch and sometimes 12 inch. This is about 20 centimeter, or even 12 inch, about 30 centimeter. So then you can make as many chip as every single die. So depend if every single chip design is here, this block is small, the area is small, then within one single wafer, silicon wafer, yeah, this is silicon wafer, you can make more chips, more IC, integrated circuits, than if you design it with larger die area. And in the case of successive approximation register, analog digital converter, because you see that the component is very few, yeah, only sample and hold, register, the DAC, and comparator, then it requires only small die area. That is why within a single wafer, you can make so many ADC IC, which result in the price will be much lower for a single IC. And there is no pipeline delay because it immediately, later we will find the other algorithm requires some pipeline. What is pipeline? Later I will explain. That is some queuing, like a queuing. Now here is every analog input immediately is being converted, approximated, every depending on the resolution, then goes to the next analog input. The trade-off is, the drawback is, however, it has lower sampling rate because of this recursive algorithm. Okay, later we will see that some other algorithm can be faster than SAR, than SAR analog digital converter. So some typical application is for instrumentation, let's say biomedical instrumentation included, but of course, which does not require very fast sampling. Okay, so maybe it is sufficient enough. Let's say for ECG, for EMG, something like that. Can be used also for industrial control and data acquisition. Okay. Now, second algorithm, this is pipeline sub-ranging ADC. So we mentioned the word pipeline now. What does it mean with pipeline here? So conversion is divided into discrete stages, thus causing the pipeline delay. So the first stage ADC is 6-bit flash, yeah, and the second stage ADC is 7-bit flash. So the total resolution is 12 bits, yeah, 6 plus 7 minus 1. Why is minus 1? Because that 1 bit is being used for error correction. So it is divided into two stages. Yeah, there are two sampling and hold amplifier here, SHA1 and SHA2. So after it goes to the SHA1, so the first, it is divided in the first part, the first portion of the analog input will be converted using the 6-bit ADC, and the second part will be converted using the 6-bit another 7-bit ADC. So here the value is then compared using DAC as well, yeah, and then the error will be amplified again here. And oh yeah, sorry, this is the comparison. Then the second stage is here using the 7-bit ADC, yeah, in a third sampling and hold amplifier. So the one single bit is used in this error correction logic, and finally the output goes through this output register. So from here you can see that it is more complex than successive approximation. Okay, so if you have, for example, an analog input here. So this is an example for 1, 2, 3, 4, 5, 6, 7, 8. So 8-bit analog digital conversion. Okay. So first, this value will be divided. Okay. If we zoom in, so the first conversion will convert 6-bit. So divided into this is 8-bit, yeah, divided into 4-bit, yeah, 101. So maximum until 101 is 4 plus 1, 5. 1, 2, 3, 4, 5, right? until here. Until here. So similar, let's say consider it similar like successive approximation to get 101. But actually it will use flash, yeah, rather than SAR. Yeah, as mentioned here, flash 6-bit flash. Later we will discuss about flash ADC. Then the remaining part here, the remaining analog input here, it will be zoomed in and then perform another second conversion to get here. So this is the value is a little bit below the half of the value of the 1-bit here. Yeah. So then it will reach 1, 2, 3. Yeah. So 0, 1, 1. Yeah, 0, 1, 1 is 2 plus 1 is 3. So then finally the final conversion will be added between the first conversion and the second conversion. The advantages, as you can see, that because the remaining value is being zoomed in and then converted into the in the second stage, it has higher resolution at high speeds. Yeah, it can reach 14 bits at 105 mega sampling per second. If you compare with the SAR, yeah, which is 12-bit at 1.5 mega sampling per second. And this is, we can have with pipeline 14-bit at 105 mega sampling per second. So hundreds times faster than SAR. Digitized wideband inputs. Yeah. However, because it requires more sampling and hold amplifier, more ADC, 2 ADC, and 1 single DAC, then it requires more power. Okay, that's why it has higher power distribution. Why you should be concerned of power? In some application, you need to calculate the required power because, for example, if you design a wearable application, it will be completely different than if you design something which is placed in the clinic or in portable application, right? In the clinic, where it is completely plugged in to the electric socket, then you don't have any too much concern about the power your circuit requires, right? But the minute when you make it portable, something that can be brought to the field, then you need to think more that the power should be less because it will require battery or solar cell, let's say. Then how can you extend the lifetime of the instrument before, not the lifetime, what do you call it, before it needs to be recharged? And of course, besides thinking of uh, enlarging the battery capacity, what you can do is try to minimize the power requirement of the circuit. Then the power requirement will be more critical if you make that thing to be wearable, for example, that instrument to be wearable. Yeah, in to be something wearable, then you cannot bring too large battery, right? Because it will be then too heavy. Then definitely you have to make a low power instrumentation. So this thing is not that suitable. This pipeline sub-ranging ADC is not that suitable for wearable application, for example, because of the higher power dissipation, and also due to the fact that it requires more subsystem, let's say compared to SAR ADC, then it requires larger die size in the chip development. So then the chip also will be larger than SAR. So that's why if you see the application, it is used for big instrumentation, yeah, for communication, yeah. Medical imaging here, the big instrument, CT scan, MRI, ultrasound, the one that is put in the clinic, and also radar. Radar usually have large size. Okay. Okay. The third algorithm or architecture which we are learning, which we are discussing, is the flash or parallel analog digital conversion. This is one of the fastest analog digital conversion. So why later we see? So instead of recursive like the SAR, it does the in flash, it does the conversion in parallel. Immediately the analog input is divided into this voltage divider circuit with resistors, and then each of the value of each of the voltage, yeah, because the voltage at this particular point will be depends on the voltage division formula. Yeah, this resistor until the ground divided by the total resistance multiplied by the total analog input. Then this value is being converted, yeah, using this comparator, yeah, and then at the same time becomes digital value. So if you have n at the resolution of ADC, then you will need 2 power n minus 1 comparators to form the digitizer array in this one. Yeah, so this is an 8-bit analog digital converter. You require 1, 2, 3, 4, 5, 6, 7, 7 comparator. Analog input is supplied to one side of the comparator here. Then one least significant bit reference ladder voltage is applied to the other inputs. One least significant bit reference ladder voltage. Yeah, this part. Okay, so this is the reference. So the reference voltage. Then it is divided. The reference voltage is divided into this voltage divider. Then this will compare the value. Okay, compare the value of the analog input with that particular voltage from the particular ladder resistor. The comparator array is clocked simultaneously and decides in parallel. The output logic converts from thermometer code to binary. Okay. So the advantages is it has the fastest conversion time because everything is done in parallel. In successive approximation, it's done recursively, right? Serial. So first approximate as with the most significant bit, then after that in the second clock with the second bit, the third clock, third bit, etc. With pipeline, a little bit faster, but it is being divided into two. Yeah, the first conversion and the second one is zoom into the remaining value, and each one using flash. So it is fast, but it requires more time because it has these two stages. With flash, it is done at the same time. With one single clock, you immediately obtain the value of the digital bit from the analog value. That's why the sampling rate or the conversion rate can go up to 1 giga sampling per second. So almost 10 times of the pipeline and maybe almost 1 million, almost 1 million times, 10 times, yeah, 10 times, not 1 million times, 1,000 times of the successive approximation and 10 times of the pipeline ADC. Low data latency, there is no delay. Yeah, data latency means here refer to the delay. With SAR or pipeline, if your data is very fast, your analog input changes very fast, then you may lose some of the data because the next conversion is done after several clock, right? In the case of flash, it is very fast. Yeah. The trade-off, however, then it requires higher power consumption because you require this so many comparators at the same time, clock at the same time. So each of the comparators will work at the same time. If the more resolution you want, then the more comparators, then the higher power you will require for your flash or parallel ADC compared to, for example, a SAR, which require only a single comparator. High capacitive input is difficult to drive. Typical application for video digitization, because video is normally a frame. Yeah, in a frame is two-dimensional data, two-dimensional analog data, happens at one simultaneous time, one time. Yeah. So every time, certain period of time, you have this two-dimensional data. So it requires very fast digitization. If you want to digitize this, the best is to use flash or parallel ADC. Other application is very high-speed data acquisition. Okay, then the fourth algorithm or architecture is what we call a sigma delta analog digital conversion. So this is also quite popular recently. So this is how it looks, the algorithm. Yeah, so we have this one big block of sigma delta modulator, and we have then a second block, sub-block, a digital filter and decimator, okay, with certain sampling frequency. So the input here is compared here, yeah, with the DAC. Yeah, the DAC goes from based on the reference voltage of that ADC, and so similar like approximation, basically similar but a little bit different. And with one bit data stream being converted to analog, then being compared, the error will be integrated, and after that another comparator. Then after digital filtering, then it will come up with the value, with the digital value. So I think this is not not necessarily related with sigma delta. Yeah. So in the first one, using Nyquist operation, we know that the sampling rate has to be at least twice the highest highest frequency component of the signal. Okay, and the quantization noise will be Q divided by square root of 12. Q here is this significant bit. Then if you do oversampling, then your sampling frequency is K multiplied by Fs plus digital filter and plus decimation. Then here is your sampling frequency, oversampling. Then you can remove some noise. Yeah. So another oversampling plus the sigma delta modulator. Okay, the remove noise will be even larger. Yeah. So you do oversampling K time of the required Nyquist sampling frequency, yeah, and then you put it in the sigma delta modulator. You do another digital filtering plus decimation. The remove noise will be much more compared to the previous one. Yeah, yeah. So larger remove noise. So then the effective resolution will be calculated using this formula equals to the logarithmic of 2, base 2, full scale range divided by the RMS noise in bits. Noise-free code resolution is similar but divided by peak-to-peak noise rather than RMS noise. And the relationship between peak-to-peak noise and RMS noise is calculated using this formula. Peak-to-peak noise equals to 6.6 times the RMS noise. Okay, since time is up, let's so the noise-free code resolution is calculated using this formula. Yeah, base 2 logarithm of the full scale range divided by 6.6 times the RMS noise. So here, then we can also calculate the effective resolution. So the advantages of sigma delta here compared to the other algorithm or architecture is it can have high resolution and accuracy, yeah, up to 24 bits. Previous algorithm usually we mention 14 bits, 12 bits, or less than it, yeah, 8 bits. But with sigma delta, accuracy can be improved, high resolution can be improved up to 24 bits. Action DNL and INL performance, yeah, remember this is the dynamic performance of the ADC discussed in the previous session. Then noise shaping capability, as we have discussed. in this part there. This part, it can shape the noise and remove the noise accordingly based on the this algorithm. The trade-off, however, is it has limited input bandwidth, so you cannot put a signal which is too high. The bandwidth is very wide, and very, for example, like imaging. For example, imaging requires very, uh, especially with high-speed imaging, with the continuous imaging, you require two-dimensional, maybe the uh, very big data, and then you require very fast image frames. Then sigma delta AD converter will have some problem with that, because remember that the algorithm in sigma delta, you do oversampling of the signal. Yeah. So, but if the signal itself has already very high bandwidth, yeah, so big bandwidth, then it is not possible to do very high sampling rate. So that's why the sigma delta ADC also has lower sampling rates compared to, let's say, for example, parallel. So the application will be if you require precise data acquisition, but not too fast, with the not too fast signal. Okay, so with imaging maybe a little bit difficult, but if you want very precise data acquisition measurement, let's say maybe EMG or brain signal with or other biomedical signal, which require precision and accuracy, but the dynamic of the signal itself is not too high. So most of medical instrumentation can use sigma delta ADC, but for imaging, then they require faster sigma delta, especially continuous imaging, 4-dimensional imaging. Like when now it's quite common to have 4-dimensional ultrasound, which can image not only 3-dimensionally the image of the body, but also can can image also successively with time. How does the structure inside the body change? This require different ADC, faster ADC. With high-speed ADC, time domain specific considerations are as follows: the aperture jitter and delay, the ADC pipeline delay. Yeah, as we discussed already with pipeline algorithm ADC. The duty cycle sensitivity and the DNL effect, the dynamic nonlinearity effect. So this is the effect of aperture and sampling clock jitter. In jitter, is most systems assume the signal is sampled uniformly at the same period. Clock noise, however, leads to non-uniform sampling. So the noise from the clock circuit itself, yeah, the timing circuit. Yeah, so it doesn't happen exactly at the same period of time. Sometimes it shifts a little bit. So in that case, then you will have some output uncertainty or noise. And then here, yeah, because of this variation, sample time variation due to that jitter, then what you want to sample will also be shifted. Yeah, so there's an output uncertainty or noise. So the jitter will leads to the degradation of signal to noise ratio when the frequency of the inputs gets higher. And when you want to sample or convert high frequency input, then SNR will degrade. So as expressed in this formula, 2 pi FA TJ FVP is less than voltage least significant bit. So this graph shows the SNR due to the aperture and sampling clock jitter. The signal to noise ratio will get smaller when you have this one, when this the jitter time, the time of the jitter gets larger. And this is when the time of the jitter is, the clock jitter is 1 picosecond, then you still have 100 decibel signal to noise ratio. But when it gets larger, the clock jitter becomes 1 nanosecond. The inaccuracy of the sampling, then your signal to noise ratio decreases to a little bit more than 40 decibel, depending on also on your input frequency. When your input signal has higher frequency, for example, up to 100 megahertz, the signal to noise ratio will even decrease furthermore. Okay, so here with, let's say, even with 1 picosecond of jitter, with 100 megahertz of input frequency, then from 100 large, more than 100 decibel, it decreases to a little bit more than 70 decibel of signal to noise ratio. So this is the effect of clock jitter, inaccuracy or noise in the clock. Then there is another variable called as the effective aperture delay time. So this is not an issue in frequency domain application, but may vary slightly among devices of same product due to variation in the sampling and hold bandwidth and clock propagation delays. So when you then ADC latency, this is especially a problem for high frequency input when our signal input signal, the analog signal, has high bandwidth with very high frequency input. In many high-speed ADC, such as sub-ranging type, in the pipeline architecture, the second algorithm or architecture we had discussed, the pipeline is used to reduce the chip size because it is divided into two different ADC, right? And also reduce the power consumption. This will allow multiple samples to be converted simultaneously in analog digital conversion and results in fixed delay between sampled input and corresponding digital output. So there is a fixed delay, what we call as the latency, yeah? The delay in between the input and the digital output. So this is an example. This is, for example, the analog input. Then you have here the sampling clock. Okay. Then the data N, this one only will be obtained after 3 clock has passed. So here, when it is clock at the end, this one, the data still displays the N-3 clock before it. So this is what we call as latency, yeah, or delay, pipeline delay. Then there's another parameter called as duty cycle sensitivity. So when high-speed ADCs are often sensitive to the duty cycle of the clock input. Duty cycle is what is the percentage of the switch on compared to the whole period of that clock, yeah, of that pulse. Clock oscillators are usually specified as 40 to 60 duty cycle or 45 to 55. Digital specification of datasheet provide a minimum clock high or low period in nanosecond to achieve rated performance. Some datasheets show signal to noise ratio and THD. Yeah, what is the time harmonization? I forgot that this is in the last, not in the today, but in the previous session of ADC, the one of the performance of ADC as the function of duty cycle. So ADC also has minimum specified sample rate. So here, depending on the clock, your clock circuit, yeah, then you can have the variation in, for example, here in CNAT, signal to noise, and then also in the SFDR ratio, in the CNAT SFDR versus the duty cycle. So usually you want this to be quite high, then you want the duty cycle somewhere around here. So this is about 45, 50, 40, 60, or 45, 55, yeah, this value. Okay, so it means 45% on, 55% off, something like that. The DNL errors will limit the ideal noise and spur floor performance. So ideal ADC code transition are exactly one least significant bit apart. Okay, 1 bit at the digit conversion. Yeah. So DNL is the deviation from this value. So for example, let's say if you have 8 bits, one least significant bit is then means 1 over 256, right? 8 bit is bit too big. Let's say 3 bits, 3 bits. So one least significant bit will mean 1 over 8. Yeah, let's say you have full scale of 0 to 10 fold, then one least significant bit equals to more or less 1.25 fold. So DNL is the deviation from this value, yeah, this transition of 1.25 volt. This will result in additive noise or spurs beyond the effect of quantization, and it will limit the ultimate achievable signal to noise ratio and low level SFDR performance. It is predictable for a given device once the error transfer function is known. The DNL error pattern varies among devices of a given product. The dynamic correction techniques include adding jitter or element shuffling to correct the noise due to this DNL. Yeah. So here when SFDR is disabled, yeah, you have this one varying INL. Yeah. But when it is enabled, you have more or less stabilized, yeah, about the zero value. So this is an example of datasheet specification. Yeah. So this is for 9430 ADC. So here the resolution is 12 bits. So in 12 bits, then the first K range will be divided into 2 to the power of 12. Or how much is that? I think is anyone? 8,000 something, yeah, if I'm not mistaken. 8,000 level something. 10 bits is 1,024, right? 12 bits is about 4,096. So for yeah, 12, yeah, so the 4,096. 12 bits is 4,096 bit. 4,096 level. So the accuracy here is given here. The DNL, the differential nonlinearity, and INL, integral nonlinearity, is given in terms of the least significant bit. Yeah, so plus minus 0.3, for example here. The temperature drift is also given. The reference value so is here uh, every least significant bit, yeah, 1.235 volt, but can between 1.15 until 1.3 volt with a typical value of 1.235 volt. This is the output value. Then the analog inputs, you can implement this analog digital converter either as differential input voltage range, yeah, with the full voltage of 1.536 or 0.766 volt. This is the input common mode voltage, input resistance, and input capacitance. This is the dynamic performance, signal to noise plus distortion ratio, SNR, signal to noise ratio at specific temperature, at specific input frequency, 100 kilohertz. Yeah, of course, if the frequency higher than this, then you get lower signal to noise ratio and lower signal to noise plus distortion ratio. Total harmonic distortion, THD, peak harmonic or spurious noise, SFDR, etc., including the jitter, how many tick second here, depending on the version, A, B, or C, it could be 30 picosecond or yeah, all are 30 picoseconds. The delay, aperture delay is 10 nanosecond. The DC accuracy here is 12 bits. Yeah, INL is given here in terms of the LSB. The offset error is also given, gain error is also given. The analog input voltage range is also given, 0 to VDD. So VDD will be the power source that connected to this ADC. Yeah. So if you input 10 volt, then the input voltage range will be 0 to 10 volt. Okay, so that is one example of ADC from one particular manufacturer, analog devices. Yeah, even having said that, the most of the principles can be also implemented for other analog digital converters made or manufactured by different manufacturers. Okay.